So let's go back to our main routine now to see what happens once we've got the letter from the table. The first thing we do is we store whatever came back in the W register into one of our GPRs, the GPR at address 072. We then clear the W register because we're going to perform a math function to test whether or not we came back with a hex 00 in the W register, which we designed as the marker for the end of the table. So if it's a 0, we don't want to write that to the LCD display, so we'll check that first. What we do is perform a logical operation between the binary number we came back with from our table and the 00000000 that is currently in our W register. Logical operations work just like the logic gates we discussed in lesson 4. We can perform an AND function, or an exclusive OR function, or an inclusive OR function, which is really just an OR function. So for example, if we have 11010011 in a file and 01011000 in the W register, and we perform an AND function on the two, we'd get a 01010000 coming out. It's like the processor puts an AND gate in between each bit in the two registers and spits out a result. An exclusive OR function would spit out 10001011. An inclusive OR function is just an OR function, so if any bit is high, it spits out a 1 on the corresponding bit. So we'd get a 11011011. In our case, we are using an inclusive OR function, IORWF. So we're putting an OR gate between each bit in the W register and the file we called, which in this case was our GPR at 072. Now we only care if GPR 072 is a 0 because that's what we're using to mark the end of our table. If any bit in GPR 072 is high, because it is ORed with the W, then the logical math function will spit out a 1 on that bit. We have that comma 0 on the end of our instruction, telling the compiler to put the result of the logical math function into the W register. So if we hit the end of our table and came back and put a 0 into the GPR, then the entire bit will come back with all zeros, which gets put into the W register. Do you remember that carry bit I talked about in a previous lesson? When we performed a left shift or a right shift on a register, and a bit went out one end, it went into the carry bit. Well, that carry bit is only one of several special function bits in a register called status. The status register basically shows the status of a mathematical function you performed. This includes logical math functions like AND and OR. You can see the bits of the status register on page 27 of your PIC datasheet. And notice bit 2, the Z or 0 bit. Now you can probably guess what this bit does. That's right. If the result of your math or logic function results in a big fat 0, this bit goes high. So this can be very useful for a number of things. And in this particular case, we are looking to see if the number we brought back from the table was a 0. If it is, because we performed a math function, comparing that number with the 0 in the W register, if it's a match, then the Z bit goes and the status register goes high. Now all we have to do is, with our program, is to check that bit to see if it's high or not. There it is, right there. Bit test on a file, skip the next instruction if the bit is clear. We tested bit 2 on the status register, which is the 0 bit. So if we came back with a 0, this bit will be set, not clear. If we found a 0, it will jump out of this main routine and go to this label, next step. If we came back with a character of some kind, from the table, then the result of our OR function will not be 0. The 0 bit in the status register will be clear, so it will skip this next line. This test means we didn't reach the end of the table yet. We actually have a character stored in memory at GPR 072. We now need to send whatever is in that memory to the LCD display. Now we are working in 4-bit mode with the display, so we have to do two very important things. We need to break the byte into 2 nibbles, send the upper nibble first, then the second nibble to the LCD display. Now bearing in mind that if I were to send any byte to port C, the upper 4 bits of port C aren't connected to anything. So I pull a rabbit out of a hat here with a slick little trick. I use this instruction here called swap a file. What the swap function does is it literally swaps the upper and lower nibbles in a byte. It switches them around so that the most significant nibble now becomes the least significant, and the least significant now becomes the most significant. So my first character I was sending was a capital B. The compiler looked up its fancy high-tech ASCII chart, discovered that a capital B was represented by 01000010 in binary, put that number into GPR 072. We need to first send 0100 to the LCD display, and then 0010. So picture what would happen if I just sent the contents of GPR 072 straight to port C. There is nothing connected to these upper 4 bits, so they go nowhere. And the lower 4 bits would be sent to the display. When I pull off the swap function, it swaps the 2 nibbles in GPR 072, so we get 00100100. But notice in my instruction, there's that powerful little multi-step command. I have a (0) at the end. That tells the compiler to put the result in the W register, not the GPR 072 register. So if you can picture it, what has now happened is GPR 072 still contains the binary ASCII code for capital B, and the W has the same binary code, but with the 2 nibbles switched around. So now, if I send the W register to port C first, the LCD is only connected to the lower 4 bits, so boom, it's now got the upper nibble of the capital B. We pulse the E line to load it up. We then send the contents of GPR 072 to port C. But again, because the upper 4 bits aren't connected to anything, they don't go anywhere. But look at this. The lower 4 bits of the capital B are what the LCD display sees. So we pulse the E line, which loads in that lower nibble now. Boom, we just sent our capital B to the display. So that is all that these commands do right here. Once we have sent the character to the LCD display, we then add 1 to our counter, load the count into the W register, because we're going to use it in the table subroutine. Then we go back up here and go and get the next character in the subroutine. I hope that all makes sense. So once we hit the end of our first table, we get a 0, which jumps us out of the first main routine, and we jump down here to next step. Now again, you can do whatever you want here. This is what I did with the code. I set the RS line to a 0 to tell the LCD I'm going to send it a command. I then set the cursor to the first character block of the second row. This now gets me ready to write the next message on the next row of the display. However, you'll remember some of those commands took up to 2 milliseconds to fulfill. Well, this was one of those commands. So after sending the commands, we call a short subroutine. the short delay routine. This is just simply a delay like we saw before, only it counts down from 255 only once. It is just a touch over 3 milliseconds long, so it is longer than needed. Perfect. We then get to the second routine, which will go look up the second table of characters called message list 2. It performs the exact same steps the previous routine did, but loads the second table here. The random message. Now, I won't go through how it all works again, but I will make one significant point. We mark the end of the table with a hex 00. Now, I could have picked really anything for that, but 00 was easy to test for by making use of the 0 flag in the status register. For example, let's say I wanted to use the capital letter Q as the marker for the end of the table. I put a capital Q in quotations, the compiler looks up its fancy high-tech binary ASCII value, which is 01010001. So now, how would you check to see if the contents of your register are the binary ASCII of capital letter Q? Well, there's a few ways you can do it, but one way would be to use an exclusive OR function, comparing that register with 01010001. Now, I chose that number because it is the exact match for the ASCII character capital letter Q. Everywhere there is matching 0 outputs a 0, and everywhere there is a matching 1 also outputs a 0 because it was an exclusive OR function. Only one bit or the other can be high. If both are high, the output is a 0. You can now load the result into the W register, check the 0 flag, and if it's set, then you know you had the binary number for a capital Q in ASCII code. But also, pay close attention here. Notice that my last entry in the table was a 0 without quotations. This is very important. If I put the 0 in quotations, then the compiler treats whatever is in those quotes as a string, not a value. So it sees this. What do you think it's going to put into the W register? It's not 0. It's going to look up the character 0 in the ASCII chart, which is right here, and it is going to load the binary number of 0011 0000 into the W register, not all zeros. If I don't put the 0 in quotations, now it assumes it is a number, so it has a value. In this case, the value of 0. So then it would load 0000 0000 into the W register. Make sense? All right, compile the code, mess with it, send some custom messages to your LCD display, and experiment with things. Change the message in the table and experiment with the characters you send out. Now, maybe if you're really brave, you can program it to send out 2 lines of a message, wait 5 or 10 seconds, then send out another message on one or both of the rows. Have fun with that.